Okay, so now we are continuing on our conversation and moving forward into finally talking about waves. So, waves are really quite fascinating, in my opinion. There's so many different things about them that are quite neat. They range in size, they range in wave period, they range in generating force, and kind of what moves them, what causes them, etc. So, I'm excited to finally share this information with you all. So, how we describe waves, we say that all waves start as something, and all waves start as some sort of disturbance or generating force. Then we have a returning of that water to the surface and what we call an undisturbed state. So we say that that is a restoring force. And there's only two restoring forces in nature, and that is gravity and surface tension. So we talked about surface tension like way long ago when we talked about how important and interesting water is to our planet. And the really intense surface tension on our planet, again, makes water very unique. And that can keep water, down, which is so we don't have like these random pillars of water just shooting up all over the place. And so when we talk about the generating forces of water, there's kind of lots of things here. So we have the moon and the sun, which causes tides, which we'll talk specifically about later. We have earthquakes and volcanoes and landslides, right? So some sort of force kind of falling into the water. These can generally cause tsunamis. And then we have wind being wind generated waves. So our causes, our generating forces are all different, but all of our restoring forces are the same. It's gravity and surface tension. So we'll really talk about gravity when we talk a lot about tsunamis, but just kind of keeping that in mind that that is a factor here. And then what we also have here on our y-axis is our wave period. So our wave period can range from anywhere from zero point 0.1 seconds to all the way up to 24 hours. So the longer the wave period are kind of these longer, much longer waves that we consider tides. And we also have two different types of waves in a sense where we have surface waves. So these are generally created by wind motion. And then we also have internal waves, and these are generated by density differences, which tend to be much larger. Things like tidal waves, turbidity currents, passing ships, and things of that nature. In one of our labs, we had that divider thing, and we flipped up removed the center divider, and then we could actually see the internal waves between those density differences. And that was a really cool experiment. I hope that you were able to view that in person. If not, let me know. I have a video for you to help with that. So the table that I have here is different from the table that you have in your book. But here's the table that you would see in your book in terms of wave summary. So it's very similar in that it has the types of waves and the causes and also the wave period, but it also has some other things here like the classes of the waves. Are they shallow water, deep water, or are they somewhere in between? What's the general open ocean height of these waves? What's their coastal height of these waves? And also their speeds and group speeds and orbital type. So it's kind of interesting here. And then on the very bottom, it kind of shows a similar schematic to what we saw on the previous slide, looking at the wave period and just generally the different types of waves. We also have things called capillary waves, which are really small wind waves. Those are kind of like the really itty bitty waves. If you go out like to the bay, if you go to the Bay Bridge and go and like look out on the water, you can maybe kind of see like these little itty bitty ripples. Those are capillary waves. And then we have, of course, our common wind waves, which those are the ones that are crashing up on the shore. Like if you've ever been to Lake Tahoe or some of those bigger bodies of water and you've seen waves and you're like, whoa, that's kind of crazy. Those are generated from wind, kind of nuts. And then, of course, we have storm waves and tsunamis and tide waves as well. And I'm going to be really careful to try to not say tidal wave because that tends to have a different meaning. So I want to also look at an anatomy of the waves here. So this is looking at, starting on the left, we have our direction of travel of these waves. So the top of the wave is called the crest. The bottom of the wave is called a trough. And the distance between the crest and the trough is called the wave height. And then the distance between the crest of one wave and the crest of another wave is the wave length. And we also have some other terms here, the wave frequency. So this would be the number of wave crests that passed a certain point per second. And then we have the wave period. So the amount of time it's required for the wave from point A to reach point B. Some other things here would be steepness. So the steepness of the wave is actually going to come into play when we talk about when waves break and how waves break. When that happens, it actually mathematically has to deal with the steepness of the wave, which I find to be quite fascinating. And I want to just also mention here the calm sea level. So generally, if there were no waves going on, this is what we would observe. This particular level here would kind of be like the in-between. So I also want to mention that waves are the medium in which energy is passing through. So there's really not actual water that's being moved here, which is kind of a funky concept perhaps. So there's this actual circular orbital motion. So as this wave passes to the right, as it's moving through this area, notice how the ducky is going up one wave, and then it gets to the crest, and then it turns down the other side of the wave. And if we were to look at the actual motion in the energy, it literally makes a circular sort of motion here. So it's really kind of weird to think about it this way, but the water doesn't move. The water doesn't do the traveling. It's the energy that's traveling through the water. It's really, really weird, but if you've ever kind of spent any like time in some ocean water and you've kind of felt it like move you from side to side and kind of go either being sucked out or being pushed in, that's the energy that's moving you. Yes, water is kind of sometimes moving within that, but it's more so the energy that's moving through the water. Kind of fascinating. And a really important point as well. So when we're considering different types of waves, we're considering their wave speed, and these vary depending on the type of wave and the water depth. So we have different types of waves here. So we have a deep water wave, which is defined as the depth of the wave being greater than or equal to 1/2 of the wave length. So remember, wavelength is from crest to crest. So the water is then deep from the wave's perspective, not what we would consider deep, right? What humans consider deep is not what waves consider deep. There is a big difference here. So it's something to really keep in mind. And then we have shallow water waves, where the depth of the wave is less than or equal to 1/20th of the wave length. So thus the water is shallow from the wave's perspective. And then as the wave approaches shore, it's starting to feel the bottom of the ocean sometimes. And so we would consider that to be an intermediate or transitional wave. In labs, we're going to be doing several calculations on this to kind of compare these arbitrary numbers and kind of determining if things are deep water waves or shallow water waves. And also, just a little nugget of information here is some waves may trick you in whether or not they are deep or shallow. So keep that in mind, because we're going to talk about a particular wave that you're like, well, it's definitely a deep water wave, and be like, tricked you, it's a shallow water wave. So when I'm talking about the energy reaching the bottom of the ocean, this would be what I mean with a deep water wave. So we have our wavelength here, and remember we have that circular orbital motion going down the water column. And if that energy dissipates and that energy is negligible at half of the wavelength, then it would be considered a deep water wave. And also the speed of the deep water wave is also determined by the wavelength and the wave period. And we'll get some practice with these calculations as well. So don't worry, this won't be the last time you see these, or worry if you really hate math, but don't worry, we'll walk you through all these calculations step by step, I promise. And then this would be still a deep water wave, sorry. So the deep water wave sets water particles in this circular sort of motion here. This orbital diameter decreases with increasing depth, right, until there's no motion below half of the wavelength, that's what we call the wave base, by the way. So where we have the lack of motion now is where the wave base is. So that's a whole another little piece of vocabulary to put in here. So we have crest, trough, length, height, and wave base. So we're just really adding things on here. And looking at the speed of these deep water waves, again, it's a huge factor with depth. So looking at this graphic here, we have wave length on our x-axis and wave speed on our y-axis in meters per second. So we can see that with these like shorter, with the smaller depths, with the shallower depths, there's only a certain speed that it has to like level out on, right? It doesn't just continue going on and on forever, amen. It levels out at a particular speed. So for example, for this 1 meter water depth, the wave speed can only travel at like 3 meters per second. It can't go any faster than that. But the water depths of these greater depths have a faster wave speed. And then thinking about these things called like the different types of waves, I guess I should say, or another factor of waves would be that of wave energy from storms, right? We've had experience with some hurricanes this semester, and so some things that I think I tried to say is even if a storm is not right on top of you, that energy from a far away storm can still reach the coastline. So basically, if you have a big old storm, there's still this sort of direction of motion and energy going through the water at the surface that eventually will kind of dissipate out and become this longer period, and we call those swells. But the closer you get to the wave center, like the shorter the wave period, basically, which makes sense. Like you're over stronger wind movement, so you're moving water more out of the way here. And then the last thing I want to leave us with is kind of wave interactions. So we have things called group speed. So ripples with these longer wavelengths move out faster than the waves with these shorter wavelengths, and then they end up dispersing. So these then front-running waves disappear and a whole new wave appears at the back of the group. So that's what this is trying to show here on the bottom right-hand side. So we have throughout some time, we have these 4 waves, and then sometime later, wave 1 disappears, wave 5 comes in the back. Sometime later, wave 2 disappears, wave 6 appears in the back, and we would see that as the group of waves kind of continues through the water. If you're familiar with surfing or body surfing or whatever, boogie boarding, oftentimes those waves come in sets, and if you've heard of that term before, then that's kind of what that means. And then the last thing I just want to quickly end us with is wave interaction. So when you have 2 waves that come together and they're coming together crest to crest, it can actually make the wave seem much bigger. And then if you have 2 waves coming together kind of at an angle where the crest and the trough interact, then you have this sort of like cancellation of that energy, which is really fascinating. And it brings forth this idea of square waves. So if you've ever seen this before, that's literally just 2 waves interacting with each other with the crest and the trough coming together. And then maybe you've seen waves kind of get bigger. I've seen it before in Hawaii, like right along the coast. You have this wave motion coming into the shore and breaking on the shore, but then the energy travels back, and then it can make some of those resulting waves much bigger. I'll try and find a video of that, and if I can, I'll share it with y'all. So with that, we'll return in person back later this week, and thanks for watching, and I'll see y'all soon. Bye!